This is Algebra 1, Lesson 5 of Term 2. We're going to start with the Desmos activity, where kids are going to be introduced to the 6 parent functions we're going to study. Constant is really not one I usually put in the list, but I went ahead and put a constant parent function in this list. And then we're going to do quite a variety of activities here. We've got a 3-act task, we've got some team tasks, and graphing, and 2 Desmos activities. So let's take a look at the first one. This activity introduces the students to 6 different function families and their characteristics. So the students are going to sort their cards into 3 families. So I'm not really telling them what to look for as far as characteristics, but hopefully it's pretty obvious which ones look similar and which ones are different. And once they've got their 3 families, they'll come over here. It'll tell them how many cards are sorted correctly, and they keep doing that until they get them all. And once they get them all, then they go on to the next slide. So this one now is going to define what these functions are. Linear functions are pretty easy to recognize. At this point, they should already know that they're straight line graphs. But which of these is the linear parent function? Now you probably do need to remind them a parent function is the most basic of all the linear functions, and you can use the parent function and change its slope and move it up and down, left and right, but it's still, the parent function is the most basic, so they are supposed to know this one by now. And then we are going to go on to the absolute value. Now we want the most basic absolute value parent function. Now only 2 of these are absolute value, so they're looking for the one that's most basic. And then finally they have the quadratic. Well, there's only one quadratic. I did put the graphing calculator icon in here so they can type this in if they're not certain what they're looking for. So do tell them if they need it to use the calculator. Please take a look at the show notes or the teacher moves. I've put in some text in there of things you might bring up or mention or ask the kids about as you go through these. I would probably not talk a lot initially, though. You might want to pace them up to that 4th slide and just see what they do before you interject, because from my experience, they do pretty well figuring it out. They're good at noticing things that are different and the same about the graph. So here we have 3 families. They're going to sort these into 3 families. And then once they've done that, it'll tell them if it's right or wrong. And then I'm going to basically give them the equation and the name of the function family. So square root is the family. The parent is y equals square root of x. And so only one of these fits that equation. Again, they have the calculator if they need to graph it to see it. And then exponential parent function. And it talks about, a is usually a positive integer, but it's sometimes between 0 and 1. We have exponential decay functions. They'll learn about that later in the course. We're just doing the parents at this point. And then the constant parent function is y is equal to some number. And then they are going to pair them. Once they do all of them, they're going to put them together. All they have to do is find the graph and put the name with it. The purpose of this lesson is really to get them just comfortable with the vocabulary, like the names of the functions and some of the basic characteristics of the functions of each family. And so that's it on that one. And then finally, there's a couple more slides with questions. Here's an absolute value function. I'm asking them to use the line tool to sketch another absolute value function. This is going to tell you a lot about if they get it. It's a V-shaped graph. They've already been working with these in the prior lessons, so they probably remember the V-shape from that assignment. But they do need to make some sort of absolute value function, try to make it different from your teammates. They can compare graphs, talk about it, and what do they all have in common. So I've given you some samples here. They're shaped like a V. They're made of straight line segments. You may notice the domain is all real numbers and the range is never all real numbers because it can't go up and down forever. It could go down forever. It could go up forever. It just can't do both because it's going to have a stopping point. And that term, this is a vertex, so they're going to learn this language soon. In fact, they learn it on the next slide. Here's some examples of graphs that do have a vertex, but not every function family has a vertex. So how would you define it? So I'm asking them to tell me, what do you think it is? A high point, a low point, the top of the mountain, the bottom of the valley? I mean, you hear a lot of things like that. Be pretty flexible at this point. We're not being too formal here. We're just getting an intuitive understanding. But they should notice where it is, because you're going to be using that language quite a bit going through the course. And then here's an axis. An axis of symmetry is not usually visible, but if it is visible, it's usually dashed. I tried to match up the color so you could know which axis goes with which one of these, but based on this graph here, what would you say is an axis of symmetry? And I've given you some sample responses and some teacher moves, so be sure to check on that. And then here, these functions do not have a vertex, and they do not have an axis, and why not? So you could talk about, there's this graph's like going up on the left side, but it's not going up on the right side, so there is no one low point. Lines don't really have symmetry like this. Some people would argue that a horizontal line has symmetry and you could use the y-axis, but you could also use the point up here. I mean, the left side matches the right side, so it's kind of hard to point one point as the center of that. So have those discussions, encourage conversation. The key is to know what vertex axis means. And then the fun. They're going to use a polypad to use some of this language. So like I said in the earlier polypad activity, or the polygraph activity, when they use any one of these words, put it up. You could have a running list going up on a screen, and you could just add the words to that list as you hear them said by students. You could add them to the board. Make a big to-do of it. The more language they're using, vertex, axis of symmetry, linear, quadratic, absolute value, constant, square root, increasing, decreasing, vertex, I said that already. Anyway, I put a long list of possible words that kids could use. And here's some questions you might hear. We kind of hope you do. You'll hear things like, is it going right? Is it going up? Is it going down? Those are very vague. And you might even pause the game and talk about that. What do you mean going up? A lot of graphs go up in both directions, like off to the left and to the right. They'll go up on both sides. But just saying that it's not very descriptive. How could we say that better? So here's some examples of questions that are good. When you hear a really great question, make note of it and point it out to the class. So-and-so asked this really great question. I love this question. Let's talk about what's great about it. Let the kids offer their insight about that. So it's a lot of fun. Love this activity. I think it'll be fun. It'll take you, depending on your kids, a minimum of 30 minutes. I have the entire lesson scheduled for 2 to 3 days, and this activity should take you at least half a day or longer. Now this next piece is super fun, and you can really you could spend a lot of time on this if you want to. If you have time, I recommend it. I've had students make videos. I always have kids take pictures of themselves creating these with their bodies. And there's also the parent function dance. I have a video that I've created for you where you can play it and they can try to keep up with the video using their arms. It's hilarious. So let's look at it and see what I'm talking about. So you'll see in these graphs the different representations, the graph, the equation, and the name of the parent, and these speed up as they go through the video. Now, when you get back to the slides, they're going to basically create the linear parent function, and they're going to insert a picture of themselves on this slide making the function. So here's an example of a student who created the quadratic parent function and the absolute value parent function with their bodies. You may notice in the background I have a video playing, and that was playing while this was going on. It's actually a way better video than the one I did, but that video also includes the sine function and reciprocal function and several others. So that's why I made a simpler version of it, but you can totally use it. There's plenty out there. They really enjoyed these. This kid right here, actually, when this kid got up and started, the rest of them jumped up and started. It's like you have to find that leader that's willing to kind of be silly, and once they're willing to do it, the rest love it. They have so much fun, but it is a challenge to get them started. They're not used to dancing around in class, so but they have fun when they do it. This was a 9th grade group. The next thing we're going to do is a function rules task, and this is actually a full lesson, but I just thought one piece of it I would pull out and use, so I'll show it to you. You may decide to do more. You may decide to skip it, and it just depends on your group. So let's take a look at it. This is the page I was interested in showing you, and these are these function machines, and they're given input-output pairs, and then they're given another page with more input-output pairs. Some have rules already stated, some do not, like this one doesn't have rules, and some, and then this one doesn't have anything, so they can create their own. So I've given you the entire thing. The way I would handle this is I would probably give one set to each team, or I might mix them up. I might give a couple of these and a couple of these to each team, and then they would get so everybody gets a variety of some that are challenging, some that are easy. To increase by 50%, what does that mean? To decrease by 50%. This is actually exponential growth, or exponential decay, but they don't need to know about that function yet. What they will discover is that some of these are linear and some of these are nonlinear, and I do ask them that question in their slides about it. So you might want to ask those questions as well, because some of these are linear and the linear ones are pretty simple, and when they're nonlinear, it does get a little interesting. And they can also do more than one rule, so they could double something and then add 3, or they could, increase by 1% or multiply it times itself and then subtract a number or something like that. So all I did was give them one slide, function machines, what is the rule? So you will determine how much of this you need. You may not need this slide at all, and you can delete it out of your slide deck if that's the case. Or you may want a different slide for each one of their machines. Like if you give them 4 machines, you may give them 4 slides, and they can insert their work for each one on a separate slide. So that's totally up to you. But this is where I would have them put a picture of their work, paper documents that they're filling out, and put those here. You can also run these off on cardstock and laminate them and use erasable markers. I mean, there's a lot of ways to handle this if you want to reuse these function machines next year. So something to think about. So I do have this lesson scheduled for 2 or 3 days, so you should definitely be in day 2 at least by the time you get to act 1 of the 3-act task. So the 3-act task is a team task involving a school bus, and so I just give them a bus and ask them, what do you think we're going to do about this bus? And then I give them this picture in act 2, what do you wonder? So hopefully they figure out at this point something to do with the seats on a bus. And that is the task. So I've given you a link out to an actual task, and the actual task used an airplane, but for my students, an airplane would not be a good task because almost none of my students would have flown in an airplane, so they wouldn't know much about how to count the seats in an airplane or what those look like. But every one of our kids has been on a bus. Even if they don't ride the bus to school, we do sometimes have buses transport them for school activities. So they've seen those. They've been inside a bus, and they would be aware of what these look like. So I switched the activity up, and they do talk about that. They'd also give some other pictures you might want to use for the bus. But to make it better for your kids, it would be good to use your own buses. So it might be smart to go take a look at one of your buses and check out the number of seats. And the goal is to create a linear function to represent either the number of seats or the seating capacity. So it's kind of up to you how you want to handle it. I'll put some information in your show notes of things you could do with this activity. But again, these 3-act tasks are very flexible. There are multiple ways you could use them, but they're really just generating a function rule for a linear pattern and then using that to answer questions about the number of seats on a school bus. The next activity is transformation of functions, and I have intentionally used the exact same transformation for every single function. The goal here is for them to notice that they're using the same numbers over and over and using them in very similar ways. So even though the parent changes and the shape of the graph is changed, the actual result of the transformation is pretty similar. So when they type their explanations, how is this being affected? They can use some of the same language on every single slide. So let's take a look at this one and I'll show you how it works. Now these are the show notes that are in for the student. So they will read these as they work, and all the slides pretty much have something down there. So they should always be looking at that. But I did link them out to a Desmos graphing calculator. I don't always do that because hopefully by now they know how to get there all on their own. But I'm going to go ahead and give them a link out, and I want them to graph the linear parent function. So they would click here, and they would start with y is equal to x. Now to tell this apart, one way to do that is to make this dash. So you would press and hold and then choose one of these options. So I'm going to choose the one in the middle, and now I've got the parent function. Now leave that there, and on the second row you're going to type in this function. They can't cut and paste it because it's an image, but they can type it in. So now I've typed in the function. Now amazingly, this is the hardest one to see because it's a line. There's no obvious vertex or something that we can look at. So they may want to actually come back to this one after they've done some of the others, but I'm going to go ahead and show you that if I go left 2 and down 5, the point -2, 5 is on this graph. They can press and hold to see the points on the graph. This line does now have a slope of 3, and that they should be able to tell that it's going up 3, right 1. So if you go from 0, 1, and you go up 3, you'll go to 4, and then over 1, you'll be at 1, 4. So hopefully they can see that, and if not, they may need to do slide 12 and then come back. If you think that's going to be a problem for your kids, you might want to switch the order and let them do 11 somewhere else. You can drag it somewhere else. So let's do this again, and this time let's do x squared, x plus 2 squared minus 5. So if they've got their graph open, that's pretty easy. They just do shift 6 and put the exponent of 2. Okay, now let's take this one and put this one in here, shift 6 and put an exponent of 2. Now they can easily see what happened. So the vertex was at 0, 0. Now the vertex is at -2, -5. So it just translated left 2, down 5. And the graph is 3 times steeper. So if they notice these points, you got a point at 0, 0, and then it goes over 1 and up 1 to get here to 1, 1. Well, if you start at -2, -5, you go over 1, you got to go up 3 to get to the next point. It's way up here. So you can actually see that it's steeper by a factor of 3. The vertex is obviously easier to spot than the steepness on a curved graph, but even if they don't say 3 times steeper, they do know it's steeper. So you might point out the 3 has something to do with that. All right, and so that's that. And then they're going to follow this same pattern for absolute value exponential. This one's kind of different because it has the 2 already. This x plus 2 is going to translate it left 2. Typing this one in is kind of a pain. You might need to tell them to put parentheses around the x plus 2 because it's hard to get that plus 2 to stay up there in Desmos without parentheses. So might need a little hand holding on this slide You could put it last and then just come in when everybody gets to that last slide and just kind of do it as a class. Square root, there is a toolbar at the bottom of the calculator for square root down here. So when they click, they can see square root symbol right there. But something else you may know or may not, SQRT will type a square root. And that's how I type it. So I show my kids that right away so that they don't have to open up the toolbar, because I don't know, I just never want to open it, the keypad. I'd just rather type it without it. So just a preference. All right, once they've done all of these slides, it would be good to come together as a class and talk about what is the 3 doing, what is the +2 doing, what is the -5 doing, because we're going to go to a function notation in the next lesson where they do 3 times f of x, maybe f of x plus 2, that quantity, and then -5. So instead of having the actual function itself, but just the notation, they can still understand that the transformation works the same no matter what the function is. And that's kind of the point of the exercise. Let's move on to the next activity. The last activity is revisiting residuals. So they're kind of doing it all again. They're going to be looking at scatter plots, correlation coefficients, and residual plots to determine if a linear model is appropriate. They are about to have a test. There are these things on here, so we do need to go back over this vocabulary. An association. What is the association in this data, and what does it reveal about Martha's savings? So they'll type in here, what is a reasonable correlation coefficient? Good time to have conversations about, does a negative correlation coefficient make sense? Is this a really strong correlation, or is it kind of weak? I mean, what do y'all think? So you can talk about that. Here they're going to actually do residuals. This isn't a sketch, so they can't sketch these in, but they can clearly see the number of spaces away. So they're trying to figure out which residual would be farthest from the line. And then here they're going to do some actual calculating. The actual value, they use the regression equation. This was on their last assessment, and it will be on the next one. So whenever they're asked to make a prediction, they will type the x value, which in this case is the days, in for x, and put their prediction. The residual is the actual minus the predicted. So it's 10 minus 9, which is 1. This will be 13 minus whatever that was. Now, the cool thing about this graph is this is y equals 3x plus 6. So if they want to use the line itself instead of typing that in, they can do that. So if I know the value of x is 3, I can scroll until this says 3, and I can see the y value is 15. So I can actually get that predicted value directly from the graph, but it's important that they know that that equation, y equals 3x plus 6, and that graph are going to give them the same result. The calculator is up here if they need it, but this is a really good screen here to kind of review many topics that they've already covered in this class. Here they're going to graph their residual plot. So this is a manual graphing instead of using the button. So these values that are in this column, they're basically going to copy those values over here into this column, and then they will have a graph. And then they can answer questions about that residual plot. Then we have one where they're going to answer, just pick some statements that are true about this residual plot. Now this is a card sort. They have residual plots that say residual on them. They have the actual data, which has the x and the y graph, and then it has R, which is your correlation coefficient. They should have 4 sets of 3 cards. Here they have a residual plot that, or 3 residual plots, which one is not like the others, and it does give them the answer, like it'll tell them yes, no, look again. So it's going to direct them to the one that is not like the others, which has like a nonlinear pattern to it. So if your data is curved or if it's expanding away from the x-axis, the residual plot is revealing your model may not be a good fit. And so that's what this one's about. And then this one, they're actually going to plot these different models over the data and decide which one they think fits the best. And it's a good time to talk about, what do you mean fits the best? Does it have to go through every single point? Well, no. Should it be close to every single point? Hopefully it'll be close to most of the points. That's kind of the goal here. And then they're going to tell me which one they picked. And here we're using the actual names of the types of functions: linear, absolute value, quadratic, exponential, square root. Is it plausible that we would create an exponential regression equation? No, it's not going to happen. But I just wanted to review those terms in this lesson, so I threw that in there. I did leave out I forgot the one. I was going to do one, and I thought, I was going to do an inverse function, and it did not. It wouldn't even do it, so, which I found interesting. But anyway, those are residuals. So good review right before their next test. That is coming next. Something I've not mentioned to you, but I did regularly, is test corrections. Here's the downside. If you do test corrections, that test has to be modified next year. So if you're going to do test corrections, you need to think about that. Because I always wrote new tests every year, but some people, that's just something they don't want to do. And I'm not guaranteeing I'm going to rewrite all your tests next year. So if you're going to do test corrections, just keep that in mind, that you're putting that data out there for the whole world to see. I usually actually post them in the hallway too. So not just my students, but other students in other classes will see all the problems that are out there that the kids missed on their tests. So something to think about. But the reason I mention it is I would always do these like right before they took their next test, and it was a really great way to revisit things they did not do well on. So even if you don't do test corrections with your kids, you definitely want to analyze the data from their last assessment and make decisions about, okay, they definitely don't know this very well. So if they have things in there that they need to revisit, like residuals, or maybe they just need to make, do linear regression again. Like, do they know y1 tilde mx1 plus b? Do they remember to type that? Is that something a lot of kids missed on the last test? You may insert a slide on this one or on a previous assignment, or even take a whole nother day of just mixed up topics so that they can practice doing those. And I would caution you, I would not give them a lot of skill practice, because not only did they're just going to remember it for a moment, it's not going to stick. It would be better to have them create something and actually use something they've created to make an equation or make a graph or, do those things that they need to know. Those are things that tend to stick a little better, and you're not having to constantly reteach the content. So this concludes the family of functions lesson. Very lengthy, but very important stuff, and a whole lot of fun. The dances and the videos, there are so many posted online because a lot of people are doing this now. Take a look at those. Get your kids to do it too. My kids had Screencastify installed in their Chromebooks as an extension. It was automatically pushed out by our district. And they had so much fun making little quick videos. And I don't have one of those. I wish I did. I don't have a family of function video, but so much fun. If you do any of this stuff and it's really fun, please take pictures. Share it with the world. Share it with me. I'd love to see it. Y'all have a great day.